Hello everyone, good evening. This is the week 10 NPTEL problem solving session for the course Robotics, Basic Science and Selected Advanced Concepts. So this week's focus was more on control, control of uh, non-linear control of manipulators, both serial and parallel. So I'll similarly to previous weeks, I'll just go through the lecture notes. I'll discuss whatever is in there. I will discuss both of the assignments, and I will record and upload this session on YouTube for further reference of students. So without much delay, I'll just quickly go through all the theory that is there in the lecture notes. So there were four lectures. One was just the general control of multi-link manipulator. The lecture two, it touched upon control of constrained and parallel manipulators, because parallel manipulators do have a constraint, so it's same class. And then there was some discussion about Cartesian control of serial manipulator. In lecture 1, it is the joint space control. In lecture 3, the focus was shifted to force control or hybrid force position control of manipulators. And lecture 4 dealt with some advanced topics in nonlinear control of manipulators, and it had mainly discussion about Lyapunov stability. Okay, so in nonlinear control, what you guys what was taught initially, like in the start, was this control of partitioning. Okay, so what exactly is control of partitioning? I will just yeah. So I will just quickly yeah. So the first thing that you studied was control of partitioning. Okay, so what exactly it said was that if like I'll take a different example from what has been given in the lectures. If there is a system, let us do this first for a one-day system. Okay, a spring mass damper system. Cx dot plus kx equal to F. Okay, so this is the equation of motion of a spring mass damper system with a force F, an external force F acting on the mass. Okay, so now since F is the external force, F is what we can apply, or F is what is applied. F is a control force. Okay, so what you do is you write F as alpha times, you can say F prime plus beta. Okay, so why we actually write it in this particular form? Okay, it will become apparent if we do not take this form and we say that we just apply a PD controller. Okay, that is, we just say that it is Kp times, let us say this is a regulation problem. Okay, so xd, not the dot, plus kd times xd dot, right? So when you write the equation of motion equal to F, okay, and let us not write the desired, let us take the actual, okay. So x and x dot, okay. So what the equation of motion now becomes is kpx plus kdx dot, that is mx double dot plus c minus kd x dot, okay. And if you say that the controller is actually minus kpx minus kdx, minus kdx, and this becomes plus k plus kp x equal to 0. Okay, so this choice of control law just changed the behavior of the system. Okay, change the natural behavior of the system. Okay, so now instead of having a damping of C, or a damping coefficient of C, it has an effective damping coefficient of C plus KD. And similarly, it has an effective stiffness of K plus KP. Okay, so you see, choosing this particular control law did not, using this particular control law, we can shape the response of the system however it is required. Okay, but for multi-DF systems, like first of all, it can be applied, but there is no mention of tracking in this, right? There is no mention of what is the state that we want to track. We have just changed the natural response of the system, and like there is only one response basically for this particular law. Okay, that if it is underdamped, it will be, something like for a for a step input, it will be something like this, right? Now this can be changed by changing kp and kd, okay, but you only get a single response always. Okay, so what we actually want to do is, if we want to specify, right, that let's say this is x and this is time, and the x should vary as this particular function that I have defined. Okay, so this function is x of t. Okay, and this is desired x, so I will write xd of t. Okay, and now if x starts from here, okay, then it should remain very close to this function always. Okay, this is x of t, the actual x of t. Okay, so what you essentially want is, if you define a quantity as e of t, that is the desired minus the current, okay, so you want e of t to go to 0. Okay, or you can say that you want to minimize e of t, but this is more accurate. So for this particular system, plus Cx dot plus Kx. If you do control law partitioning, okay, where this is F prime plus beta, where alpha is M and beta is your Cx dot plus Kx. Okay, I think I should mention one thing also. Using control or partitioning, what you get is independent of the system parameters, okay, or the model parameters that you have. Because I think I should explain this in more detail. Yeah. So I mean, you can do tracking even without the control of partitioning, okay? But control of partitioning just makes our work easier. Okay, if I said that this is minus kp, and it is the error. Let me say that this is the error, right? This is xd minus x minus kd, xd dot minus x dot plus m xd double dot. Plus m xd double dot plus c xd dot plus k xd. Okay, let us remove this pd term for now. So using this, what it will become is, it will become xd double dot minus x double dot plus c xd dot minus x dot plus k xd minus x equal to 0. Okay, and now if you write it as error, so this is e double dot, this is e dot, and this is e. So it becomes m e double dot plus c e dot plus k e equal to 0. Okay, so now this equation governs how the error will evolve. Right? Error between the desired x and the current x. But you see, this equation depends on your system parameters. Okay, so you can't you can't really change the behavior of the system without really changing the system parameters. Okay, but then if you take a look at your partitioned control law, okay, and I will directly write the alpha plus kx equal to, so alpha was m, okay, m f prime plus, and beta was cx dot plus kx. Okay, right now we will assume that these things perfectly cancel out. Okay, so what is left is this equation. Okay, this double integrator equation. Okay, or you can say equation that governs the motion of a unit mass on the application of force F. So now if you write it in the form of PD control, okay, for example, Kp xt minus x, the error, minus Kd xt dot minus x dot, and let's say xd double dot. I think there's hello Sidesh, do you have any doubts? Hello, can you hear me? Okay, so I was just going through the lecture notes of this week and just discussing what was discussed by sir, and then I will go through the assignments and just tell which part of the lecture notes are relevant. So, well, first I was going through the controller partitioning. So I think I will share that here right now as well. Yeah. So yeah, so the first lecture dealt with controller partitioning. Okay, controller partitioning because um, the final equation that governs the evolution of error does not depend on system parameters. Okay, that is the advantage of controller partitioning. And then you can choose KP, your KP and KV. Okay, depending on how you want the behavior of the system to be. Okay, usually we go for critical damping. Okay, and critical damping, the relation between Kp and Kv is this, that Kv is twice the square root of Kp. And this is how the block diagram for controller partitioning looks like. So this block diagram just represents these equations, these set of equations in the above two slides. Okay, now there was discussion on how the ideal performance is not possible. Basically, you cannot exactly cancel out these terms, right? That you are saying beta and alpha, because you don't, because it is very difficult to exactly know these values. So what you have is just you only have your best guess or best estimates of these values. So what you end up on right hand side is not zero as is in the ideal case, but a finite value. Okay, now the better your estimate is, the smaller this finite value will be, and the better your control will be still, right? So, like, okay, uh, but still, like, this introduces non-linearities in your system. Okay, like what we wanted was we were trying to linearize the whole equation, but in the right hand side, we are still left with a non-linear equation. But there are techniques to that lean can even treat this as a linear system by taking an upper bound on this uncertainty. Okay, but those have not been discussed right now. Then there were some simulation results. Then there were different control schemes, right? The results for different control schemes. Okay, like PD control scheme, and then feed forward controller with exact knowledge of model parameters, Then we considered an error of 10% in mass and 5% error in the radius. Okay, so yeah, then there were the results. I don't think I need to go through them. Okay, so for fast motions, feed forward controller, like without model in uncertainties, they will be very accurate. Okay, but that is again not always the case. But even then, even if there are some uncertainties, computer talk using the feed forward controller, using any, for example, the partition control law, even then they are more accurate than PD. Okay, because you're at least compensating for some of the nonlinear effects that are there. You won't be compensating for these 10% uncertainties, but that will be much better than compensating for nothing, as is the case in the PD controller. Okay, so what is the advantage? Talk profiles are smoother when you use a feed forward control. Okay, and you always want your all the profiles, not just talk, the position, velocity, accelerations to be smooth. Okay, there should not be any discontinuities in any of the profiles. Okay, and then there was a summary. Okay, then so like single statement on the PD controller, then the model based, and the differences. Okay, and then there was discussion on the control of uh, this pick and place robot, and this just had different equations, but this was very similar to what was discussed before. Okay, so there is nothing new in that. Okay, like the results are actually pretty like if you're seeing them for the first time, then you should take a close look at the results the that the tracked trajectory using PD control is worse than the tracked trajectory using model-based control. Should I see that? When you use model-based control schemes, the tracking error is much less as compared to the tracking error when using only PD control. Okay, then there was a control of constrained manipulators. Okay, so this was again was discussed in the lectures. So there is not much to discuss about them here. Okay, but then there was discussion on Cartesian control of serial manipulators. Okay, so Cartesian control is essentially control while taking into account the error of the end effector, position and velocity. Till now, we were only taking the error in position and velocity of the joints. Okay, so that was joint space control scheme. Now this is Cartesian space control scheme. Okay, so similar to how we wrote the equation in joint space, we can convert those equations, or we can write from scratch also, like both are equivalent things. Equations in Cartesian space or task space, as you can call it. Okay, so the variables in task space are actually the end effector position and orientation. Okay, so once you write the equation of motion in task space, then everything else is just similar. Okay, like torques are related through force by this static balance equation tau equal to j transpose F. Okay, and this mass in Cartesian space is related to mass matrix in joint space using this equation, and these are just space transformations. Okay, so this transformation takes mass matrix from the joint space to the Cartesian space, where J is the Jacobian matrix between the Cartesian space and the joint space. Okay, between X and Q. Okay, so like again here, the control law partitioning was discussed. Then this error dynamics finally was in the end effector or the Cartesian space variables, and not the joint space variable. Okay, because here we are calculating that force that should act on the end effector, and using that force, the torque is calculated using the static force balance equation or the energy balance equation, I should say energy balance. It is not force balance, right? And then there was force control. Yeah, then there was discussion of force control. Like till now, we were only concerned with tracking of the position of the either the end effector or the joints. But in many cases, it is of interest to control the force that is being applied at the end effector mostly or anywhere. Okay, so rather than discussing about position or trying to track the position, we are trying to track the force. Okay, but then there was a very simple example given by sir. You can go through the lecture notes to can see this. But what you have to keep in mind is this. Okay, so you cannot control force and velocity in same direction because of the principle of duality. Okay, now what is principle of duality? Like, again, if you go through the lecture, sir has discussed it already. Okay, so what it means is that if you want to control, let's say, yeah, take this example of robotic grinding, that the force can be controlled normal to the surface being grounded, okay, and velocity can be controlled tangent to the surface being grounded, okay. So you cannot control velocity in the direction normal to the surface while you are also trying to control the force, okay. And again, these Cartesian control schemes then naturally extend for force control because this desired force is essentially the desired force on the end effector, right? Or the Cartesian in the Cartesian space. Okay. So now for this particular task for force control, okay, the robot control tasks are divided into two subtasks. Okay, one is when it is in contact with the environment, and the other is when it is in free space. So I had paused the recording and therefore I will just go through the force control. From force control, I will go through everything again. Uh, so this force control, right till now, we have been only discussing control in the control of the position of the manipulators. Okay, but rather than position, sometimes it is of interest to specify the force that should be applied at a particular location. And most intuitive is the force that should be applied at the end effector of the robot. Okay, and like force control of end effector is very intuitive. Okay, uh, in the Cartesian space. Okay, so again, this force control examples they have been discussed by sir in the lectures, but what I would like to specify is this particular thing that force and velocity cannot be controlled in the same direction when we are talking about the Cartesian space. Okay, why? Because like they are related through power. Okay, so you have to leave one free when you're trying to control the other another. Okay, for it for the power equation to hold. Okay, like for example, when you're talking about the robotic grinding task, then the force that it applies on the surface that is to be ground, that is of more interest as compared to the position of the robot in the in this normal direction. Okay, so the force can be controlled in the normal surface and velocity can be controlled in the tangent surface. Okay, and then there was a discussion of the partitioning of tasks, like how the control can be partitioned whenever it is in contact and when it is in free space. Okay, and then yeah, like position control can be used for particular directions, and in this case, it can be used for tangential direction. in this example. Okay, and force control we use for, let's say, the normal direction. Okay, and these surfaces, okay, like whenever a manipulator is in contact with a surface, these surfaces they act as a constraint. Okay, so these constraints involve variable actually that cannot be controlled, because you see the manipulator cannot go through the surface. Okay, so it makes less like it makes less sense to specify position in that particular direction, right? It is much better to specify the desired force in that direction. Okay, and like the manipulator cannot apply arbitrary force tangent to the surface. That is why we can achieve actually uh, much better position and force control, but much better position and velocity control in the tangential direction of these constrained surfaces. Okay, because again, one of the models that we use for tangential force is the Coulomb friction model. Okay, and we know that it depends on the normal force. Okay, it cannot be arbitrarily large. Okay, and then we can also introduce some artificial constraints. Okay, for all the position and force variables that can be controlled, or that we want to be controlled. For example, if we want force control in a particular direction where there is no physical constraints, then we specify some artificial constraints. Okay, like basically we specify the equations that the robot should treat as constraints. Okay, for achieving force control or position control in that particular direction. Okay, and then there were examples of all these of this particular task. Okay, peg in hole assembly. So I will, yeah, and then there was a discussion of hybrid position force control of manipulators. Okay, again, this is just application of what has already been discussed earlier, like how it is actually implemented. Okay, what is the, let's say, the block diagram of this particular kind of control systems. Okay, but even in this case, position and force control are not in the same direction. Okay, because they cannot be controlled in the same direction. Okay, and this is uh, the block diagram for this particular, yeah, for this particular concept, like hybrid position force control. So force control is being used for a particular direction, and Cartesian position control is being used for a particular, for the other direction essentially. Okay, like, yeah, and these selections essentially, okay, that which um, directions to choose for which controller, they are done using these what are generally called selection matrices. Okay, like, yeah, here it is called selector switches. Like, yeah, so these specify the axes in which a particular uh, type of control, either the force control or the position control, should act. Okay, and then there were discussions on the topics of, like, there was some discussion on stability of nonlinear control, nonlinear control systems. Okay, or the stability of nonlinear systems in general. Okay, so the concept that was discussed in this particular section was the Lyapunov's method. Okay, for stability analysis. Okay, so what Lyapunov's method essentially says is that for any nonlinear system that can be written like this, it is asymptotically stable in Lyapunov sense. So what is Lyapunov sense? There is Lagrange stability and there is Lyapunov stability. Okay, there is uh, one more. Uh, so in Lyapunov stability, essentially the error bound keeps growing smaller and smaller. Okay, so basically a system is Lyapunov stable if there exists a Lyapunov function for that function. And what is a Lyapunov function? It is any function, okay, like a function of the states of the system that is positive definite, differential, and the first differential and the first time derivative is negative definite. Okay, so the terminology positive definite and negative definite all are being used here because this is like everything is a vector equation, vector or matrix equations now. Okay, so not it is if it was scalar, we would have just said that the first time derivative of v should be negative. But for matrices, there is no such notion of negative. Okay, there is this notion of negative definite that all the eigenvalues are less than zero, all of them. Okay, and positive definite, all the eigenvalues are greater than zero. Okay, so then there are some examples of Lyapunov functions. Okay, and there is just there are these comments on Lyapunov stability theorem that for any Lyapunov function, if v dot or the first derivative of x is negative for is just less than zero, not equal to zero, for all the states other than the equilibrium states, or for all the points other than the equilibrium points of the system, okay, then it is said to be an asymptotically stable system, or this is the condition for asymptotic stability. So, like, keep in mind that v dot can be zero at equilibrium points. Okay, all these conditions that are given here. Okay, for example, this condition, the sufficient condition for stability, and then this other condition that we will discuss now. All of them talk about the values of Lyapunov function and the first derivative of the Lyapunov function, first time derivative, for all the points other than the equilibrium points. Okay, so if for all the other points v dot is negative definite, then the system is asymptotically stable. If for all the other points v dot is negative semi-definite, okay, it means that there exists some points other than the equilibrium points where v dot can become zero, then asymptotically stable, then asymptotic stability essentially cannot be guaranteed. The system can still be asymptotically stable, but under certain conditions. Okay, and they are given by Lassalle's principle. Okay, and then again there was an example of single link manipulator. That is essentially a pendulum that is controlled at the hinge. Okay, and then again there is one candidate Lyapunov function that is given. Okay, so what is a candidate Lyapunov function? For any system, there can be multiple Lyapunov functions. Okay, any function that satisfies the three properties of the Lyapunov function, that it should be positive definite, it should be differentiable, and the first time derivative should be negative definite. Okay, or at least negative semi-definite. Then that function is called a candidate Lyapunov function. Okay, because multiple functions can satisfy all these uh, conditions. Okay, so for this example, the first candidate Lyapunov function is the total energy of the system. Okay, and in most cases, total energy is the most intuitive candidate for the Lyapunov function because it is always positive definite. Okay, but again, there can exist a Lyapunov function for a system that has nothing to do with the energy of the system, that is completely abstract mathematically, but that can give much better performance or much better control performance as compared to the uh, performance when energy is taken as the Lyapunov function. Okay, so for this particular example, okay, it will achieve asymptotic stability. Okay, like when there is no damping, there is no asymptotic stability, and it also makes sense because if you only use your like if we do not apply any torque, okay, then it will just keep swinging, okay, and if there is no friction or damping also, it will keep swinging. It should not come to rest, okay. That is why there should be no notion of asymptotic stability in this particular example. But when we add damping in this particular case, then it becomes asymptotically stable. And again, this is very intuitive that when there is damping at the hinge or the joint, the oscillations of the pendulum should die out. Okay, and that is the case of asymptotic stability. Okay, that the state approach a single value when as the time goes to infinity. Okay, now again, like this was stability for one particular, you know, uh, state. For example, specifically for when theta was 0. Okay, but if theta is not 0, okay, then the Laplace function was changed. Okay, like we just took a different Laplace function. Okay, and there was just this different change of coordinate that was used. And in this particular case, when you uh, test for stability, this will not be asymptotically stable. And again, if the desired position or the equilibrium position, as you want to say, or that like about this particular position, the function should not be asymptotically stable because the pendulum cannot stop arbitrarily at some angle, right? So that is why in this case, when your xd, okay, or theta basically is not equal to 0, the system is not asymptotically stable. Okay, and like this Laplace theory also tells you the same, as you know from the intuition. Then there were like different examples. Then there was an example of NDF manipulator. Okay, so again, in this example, the candidate Laplace function was the total kinetic energy of the system plus the potential energy of the system because of the introduced Kp. Okay, so how you actually choose candidate Laplace functions is basically you choose Laplace functions such that V dot will always be negative definite. Okay, so you choose not Laplace functions, you choose Laplace functions such that for a given control law, or again, you can say that you choose control law such that V will be positive definite and V dot will be negative definite for that specific control law. Okay, and then there was just some discussions on stability when you add the gravity term, and then there was a discussion on some advanced topics. Okay, like what happens when you have a lack of knowledge of model parameters. Okay, what happens when the system is not controllable or when it is controllable. Okay, like there is a notion of controllability of the system. So again, this was just discussed very superficially in the lectures, and but sir has again given a lot of suggested additional reading materials, and I highly encourage all of you to go through at least some of them. Okay, this will give you a good perspective of control for manipulators, okay, or non-linear control in general. So with this, I think I'll end the lecture here.